Welcome back to the session on solution of linear equations by numerical methods. In the previous session, we discussed two methods, bisection method and fixed point iteration method, to solve equations of the form f of x equal to 0. Here, we shall discuss another two methods. First one is regular falsy method and the second one is NewtonRaphson method. First is regular falsy method. Or method of false position. In this method, we first find two numbers a and b such that a less than b, between which a real root of the equation f of x equal to 0 lies, using the location theorem. Let x1 be the root of f of x equal to 0 in the interval a b, that is x1 belongs to the interval of approximation a b. We find x1, this x1 by linear interpolation in the interval a b, that is, we find x1 on the assumption that the change in f of x is proportional to the change in x. This assumption is valid provided that a and b are close enough to the actual root. Thus, f of x1 minus f of a divided by x1 minus a is equal to f of b minus f of a divided by a minus b. Since x1 is the root, we have f of x1 is equal to 0. Therefore, this expression becomes minus f of a divided by x1 minus a is equal to f of b minus f of a divided by a minus b. This can be written as x1 minus a is equal to negative of b minus a, sorry here b minus a, not a minus b, b minus a. Negative of b minus a into f of a divided by f of b minus f of a, or x1 is equal to, that is x1 is equal to a plus, sorry, a minus b minus a into f of a divided by f of b minus f of a. That is x1 is equal to a into f of b minus a into f of a negative of b into f of a plus a into f of a all divided by f of b minus f of a, which is equal to a into f of b minus b into f of a, negative of a into f of a plus a into f of a cancelled, all divided by f of b minus f of a, x1 equal to a into f of b minus b into f of a divided by f of b minus f of a. The value of this x1 given by this expression is only the approximate value of the actual root. Since the change in f of x will not be in general exactly proportional to the change in x, this is not an exact root of the equation, exact value of the root, this is only an approximation. If we take the initial approximation as x naught, we can write this expression as x1 is equal to x1 is equal to x naught into f of b minus b into f of x naught divided by f of b minus f of x naught. Assuming x1 as an approximation of the root, a still better approximation can be obtained by replacing x naught by x1. That is, we get x2 is equal to x1 into f of b minus b into f of x1 divided by f of b minus f of x1. Here x2 is the better approximate value of the actual root than x1. This process of iteration is continued till the required accuracy is obtained, that is, modulus of xi minus xi plus 1 is less than epsilon, where epsilon is a very small positive number. This is the regular falsy method. The geometrical interpretation of this regular falsy method is as follows. Consider the graph of y equal to f of x. Now, by using location theorem, we find the approximate interval a b, in which the approximate value of the root lies. Let this is a, here is b. Then we can mark the point b comma f of b and a f of a. Now, we join these 2 points, that is, we draw a chord between these 2 points a f of a and b f of b. It will intersect the x axis. This point of intersection is taken as the first approximate value of the actual root, say x1. Now, we evaluate f of x1 and find out the next interval of approximation. Suppose f of x1 is negative, then we can mark this point as x1 f of x1. Next, we draw the chord joining these 2 points x1 f of x1 and b f of b. This will intersect the x axis, which can be taken as the second approximation, say x2. In this order, we can find an interval whose limits are very close enough, which is the geometrical interpretation of this method. The equation of the chord joining these 2 points a f of a and b f of b is written as y minus f of a divided by x minus a is equal to f of b minus f of a divided by b minus a. Since this line, this chord will intersect at the x axis, the point of intersection is, on the point of intersection we have y equal to 0, that is, on the x axis y equal to 0. Then this equation of chord will become minus f of a divided by x minus a is equal to f of b minus f of a divided by b minus a. That is, x minus a is equal to minus of b minus a into f of a divided by f of b minus f of a, or x equal to a minus of b minus a into f of a divided by f of b minus f of a. On simplification, we can write this as x equal to a into f of b minus b into f of a divided by f of b minus f of a. This is the iterative formula in the Newton-Raphson method of false position. Now, we have to work out a problem. The problem is find a real root of the equation x e raised to x, x into e raised to x is equal to cos x. This equation can be written as cos x minus x e raised to x is equal to 0, which is of the form f of x equal to 0, where f of x equal to cos x minus x into e raised to x. If we put x equal to 0, we will get f of 0 equal to cos 0 minus 0, that is equal to 1, because cos 0 is 1, which is positive. If we put x equal to 1, we will get f of 1 equal to cos 1 minus 1 into e raised to 1, that is cos 1 minus 1, that is equal to minus 2.17798, which is negative. Therefore, by the location theorem, we can say that a root lies in between these two numbers, that is, a root of the given equation is in the interval 0 and 1. By method of false position, we have x equal to a into f of b minus b into f of a divided by f of b minus f of a, which is the iterative formula. Here we take a equal to 0 and b equal to 1. Therefore, we will get the first approximation as x1 is equal to a is 0, therefore, this is 0 minus b is 1, 0 minus 1 into f of 0 divided by f of 1 minus f of a, f of 0, that is equal to minus f of 0 is 1 minus 1 divided by f of 0 is 1, therefore, minus 1 into f of 0 equal to minus 1 divided by f of 1 is minus 2.17798 minus f of 0 is 1, which is equal to, on simplification, we will get 0.31467, 0.31467, which is the first approximate value of the root of this equation. Clearly, 0.31467 is lying between 0 and 1. Now, we evaluate f of x1, which is equal to cos 0.31467 minus 0.31467 into e raised to 0.31467. On simplification, the value of f of x1 is 0.51986. F of x1 equal to 0.51986, which is positive. Here f of 1 is negative, and now we got f of x1 is positive. By location theorem, we can say that a root of this equation is lying in the interval 1 and 0.31467. Root belongs to 0.31467 and 1, because f of 0.31467 is negative, positive, and f of 1 is negative. Therefore, root in between these 2 points. Now, again we use this iterative formula. We put A equal to 0.31467 and B equal to 1 in this formula. We will get the second approximation as x2 is equal to 0.31467, 0.31467 minus 1 into, sorry, A into f of b, this is A, into f of b is here f of 1, f of 1 is equal to minus 2.17798. Minus b into f of a, b is 1, f of a here is f of x 1, that is 0.51986, all divided by f of b minus f of a. F of b is here f of 1, that is f of 1 is minus 2.77198 minus f of b. F of b is, sorry, f of a is this 0.51986. On simplification, we will get x2 equal to 0.44673. This is the second approximate value of the actual root. Here, first approximate value is 0.31467 and second approximation is 0.44673. The difference between these two is not so small. Therefore, we evaluate f of x2, which is equal to f of x2 is equal to 0.20354, which is greater than 0. Therefore, by location theorem, we can say that a root lies in between 0.44673 and 1, because f of 1 is negative and f of 0.44673 is positive. We take this as A, that is A equal to 0.44673 and B equal to 1, and use this iterative formula. We will get the third approximation as x3 equal to, x3 is equal to 0.07079. 0.07079 is the third approximation of the actual root. Now, we evaluate f of x3 and find out the next interval of approximation and proceed like this. After the fifth iteration, we will get x5 is equal to in the fifth iteration, we will get x5 is equal to 0.51520, and we evaluate f of x5 and we will find the next interval of approximation. In the sixth approximation, we will get the approximate value as x is equal to 0.51692, which is the value of the approximate value of the exact root in the sixth iteration by using the same formula. Therefore, these two numbers, the difference between the absolute value of the difference between these two numbers, that is x6 and x5, is very small. Therefore, we can take the approximate value as x equal to 0.51692. we can take the approximate value of the exact root of the given equation as x equal to 0.51692. Now, we will discuss the next method, that is NewtonRaphson method or method of tangent. NewtonRaphson method. This is the fourth method to solve the equation of the form f of x equal to 0. NewtonRaphson method. Or method of tangent. Method of tangent. When the derivative of f of x can be easily found and is a simple expression, the real root of the equation f of x equal to 0 can be computed rapidly by the Newton-Raphson method. When an approximate value of a real root of equation is known, a closer approximation to the root can be obtained by an iterative process. Let x naught be an approximate value of the exact root of the equation f of x equal to 0. Let x naught be the approximate value of the exact root and x 1 be the exact root closer to x naught, so that x 1 is equal to x naught plus h. X naught is an approximate value, x 1 is the exact root, then we can say that x 1 is equal to x naught plus h, where h is very small. Since this x 1 is the exact root, we have f of x 1 is equal to 0. That is, f of x naught plus h is equal to 0. By using Taylor's formula, we can write this as f of x naught plus h by 1 factorial into f dash at x naught plus h square by 2 factorial into f double dash at x naught plus etc. is equal to 0. By using Taylor's theorem, we can expand the left hand side like this. Since h is very small, we can neglect the second and higher powers of h square, which is tends to 0, all are tends to 0, because h is a very small number less than 1. Therefore, we can write f of x naught plus h into f dash x naught is equal to 0. That is, h equal to minus f of x naught divided by f dash at x naught. From this, we can write f of x naught equal to negative of h into f dash of x naught, which gives h is equal to negative of f of x naught divided by f dash of x naught. Therefore, we can write x 1 is equal to x naught plus h is this, that is, x 1 is equal to x naught minus f of x naught divided by f dash at x naught, which is the approximate value of the actual root. Taking x 1 as the approximate value of the exact root, a better approximation can be obtained by replacing x naught by x 1. Instead of x naught, we use x 1, we will get the better approximation of the actual root. That is, x 2 is equal to x 1 minus f of x 1 divided by f dash of x 1. We proceed in this manner. We will get the general case as x n plus 1 is equal to x n minus f of x n divided by f dash at x n, which is the Newton-Raphson formula. Newton-Raphson formula. This is the iterative formula used in Newton-Raphson method. Let me conclude this session. In this session, we discussed two methods. First one is method of false position or regular falsy method, in which we derive an iterative formula to find out the approximate value of the root of the equation f of x equal to 0. The second method is Newton-Raphson method, that is the method of tangent, in which we derived Newton-Raphson formula. Thank you for watching this session.